Hysteresis loop, we need to go through hysteresis. Hysteresis is dependence of the state of a system on its history. For example, a magnet may have more than one possible magnetic moment in a given magnetic field, depending on how the field changed in the past. Another example is deformation of rubber bands and many other natural phenomena. Hysteresis can be found in physics, chemistry, engineering, biology, and even in economics. For example, in thermostats and Smith triggers, it prevents unwanted frequent switching. Hysteresis can be dynamic lag between an input and output that disappears if the input is varied more slowly, and this phenomena is particularly known as rate-dependent hysteresis. And the last thing that you should know about hysteresis is that the systems are non-linear. Okay, so I think that would be more than enough to come to our next topic, or the main topic, that is hysteresis loop. Now coming to the hysteresis loop, it is being used to study the magnetic property of a material. So point number one is that the loop shows the relationship between induced magnetic flux density, that is denoted by B, and the magnetizing force, that is denoted by H. So the hysteresis is also known as BH loop or BH curve. So this is the boss. This is how the BH curves look like. But the question is, how is it made like this? So point A, ferromagnetic material that has never been previously magnetized or has been truly demagnetized will follow the dashed line as H is increased. So from here we can say that more the current is applied, stronger the magnetic field is. So at a point A, almost all magnetic domains are aligned, or we can say that magnetic saturation point is achieved. When H is reduced to 0, the curve will move from point A to B. After magnetic force getting 0, some amount of magnetic flux remains. This point is also said as the point of retentivity. After that, when the magnetic force is reversed, the curve moves to point C, where the flux has been reduced to 0. This is called the point of coercivity. After this, the magnetic force is increased in negative direction. The material will again become magnetically saturated, but in opposite direction, or say till point D. After that, reducing H to 0 brings the curve to point E, as shown in the graph. Increasing H back in positive direction will return B to 0. On the things which you need to notice here is that the curve did not return to origin of the graph because some force is required to remove the residual magnetism. The curve will take a different path and it will lead to point F as shown in the graph. And this is said as BH curve or hysteresis loop, and this is how it works. There are number of primary magnetic properties of a material and can be determined. So we'll talk about them one by one in brief. So number one is retentivity. It is said to be a certain amount of residual magnetic field when the magnetizing force is removed after achieving saturation point. Number two is residual flux. It is the magnetic flux density that remains in a material when magnetizing force is zero. Number three is coercive force. It is the amount of magnetic field which must be applied to a magnetic material to make the magnetic flux return to zero. Number four is permeability. It is denoted by mu. It describes the ease with which the magnetic flux is established in the component. And at last, number five is reluctance. It is the opposition that a ferromagnetic material shows to the establishment of a magnetic field.